Right now, at this very moment, there are particles in your body that are instantaneously connected to particles on the other side of the universe. And I'm not speaking metaphorically. I'm talking about a real, measurable phenomenon that Einstein himself called spooky action at a distance, because it terrified him so much that he spent the last 30 years of his life trying to prove it couldn't exist. He failed. The phenomenon is real. And what's even more disturbing, when you measure one of these connected particles here on Earth, its twin particle 13 billion light years away responds immediately. Not at the speed of light, instantly, as in zero time delay. This violates everything you thought you knew about how the universe works. Here's what makes this truly unsettling. This isn't some fringe theory proposed by wild-eyed physicists in a basement somewhere. Quantum entanglement has been experimentally verified thousands of times. In 2022, 3 scientists won the Nobel Prize in Physics, specifically for proving that this impossible phenomenon is absolutely, undeniably real. Alling Aspect, John Clauser, and Anton Zeilinger demonstrated beyond any shadow of doubt that particles can be connected in ways that transcend space and time itself. But here's the real kicker, and this is what's going to haunt you for the rest of this video. If particles in the universe can be connected instantaneously across any distance, what does that say about the nature of reality itself? What does it say about you? About consciousness? About the very fabric of existence? By the end of this deep dive, you're going to question whether the universe is even real in the way you think it is. Before we shatter your understanding of reality, do me a favor. Hit that like button and subscribe to the channel, because what we're about to explore will fundamentally change how you see existence itself. And drop a comment below telling me what country you're watching from and what time it is where you are right now. I'm genuinely curious to know how far this mind-bending information is spreading across the globe. Let's start with something you think you understand: connection. When you think of two things being connected, you probably imagine a physical link, a rope, a wire, a signal traveling between them. But quantum entanglement throws all of that out the window. Imagine I have 2 coins. I flip them both, and no matter where these coins are in the universe, whenever one lands on heads, the other lands on tails. Every single time, instantly. Even if one coin is in New York and the other is in the Andromeda Galaxy, 2.5 million light years away. Your brain is probably screaming right now, "That's impossible. Information can't travel faster than light." And you're absolutely right to think that. Einstein's theory of relativity, one of the most well-tested theories in all of science, explicitly states that nothing can travel faster than light. Not information, not matter, not anything. The speed of light is the universal speed limit, approximately 186,000 miles per second. And yet, quantum entanglement seems to violate this fundamental law. This is exactly what made Einstein so uncomfortable. But here's the twist that's going to blow your mind right from the start. Nothing is actually traveling between the particles. And this is where your conception of reality starts to crumble. These particles aren't sending signals to each other. They're not communicating in any traditional sense. They're connected in a way that transcends our normal understanding of space and time. Think of it like this. Imagine you and your best friend are actually the same person, just experiencing life from 2 different perspectives. You don't need to send your friend a text message about what you're thinking, because you are your friend. There's no distance between you because you're fundamentally the same entity. This is essentially what's happening with entangled particles, but even stranger. When 2 particles become entangled, they form a single quantum system. They're not 2 separate things that happen to be connected. They're one thing that exists in 2 places simultaneously. Your brain literally cannot visualize this because we evolved to survive in a world of separate, distinct objects. But at the quantum level, separateness is an illusion. Let me give you the actual history of how we discovered this reality-shattering phenomenon. In 1935, Albert Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper that was supposed to prove quantum mechanics was incomplete. This paper, known as the EPR paradox, named after the three scientists, described exactly this scenario with connected particles. But Einstein didn't propose this as a real phenomenon. He proposed it as a thought experiment to show how absurd quantum mechanics had become. He was essentially saying, look, if quantum mechanics is correct, then this crazy thing would have to be true, which obviously it can't be, so quantum mechanics must be wrong. Here's the shocking part. Einstein was wrong. The crazy thing is true. For nearly 30 years, this remained a philosophical debate. Nobody had figured out how to actually test whether Einstein was right or wrong. Then, in 1964, a physicist named John Stuart Bell created what's now called Bell's theorem. This was a mathematical framework that could distinguish between Einstein's view of reality and the quantum mechanical view. Bell's theorem essentially said, if Einstein is right and particles maintain separate, independent properties, then measurements on these particles will follow certain statistical patterns. But if quantum mechanics is right and particles are truly entangled, the measurements will violate these statistical patterns in specific measurable ways. Think of Bell's theorem like this. Imagine you're trying to figure out if two people are secretly coordinating their answers to questions, or if they're genuinely connected by telepathy. Bell figured out the exact statistical test that would prove which one was true. And when scientists finally performed these tests in the 1970s and 1980s, reality failed Einstein's test spectacularly. Now let's get into the actual mechanics of how entanglement works, because this is where things get truly bizarre. To create entangled particles, scientists typically start with a single particle and split it into two. Here's a common method. You take a special crystal and shoot a high-energy photon, a particle of light, through it. Through a process called spontaneous parametric down conversion, this one photon splits into two lower-energy photons. These two photons are now entangled. But what does entangled actually mean? Let's talk about a property called spin. At the quantum level, particles have a property called spin, which you can think of as the particle's orientation, kind of like a tiny compass pointing in a particular direction. But here's the quantum weirdness. Before you measure a particle's spin, it doesn't actually have a definite spin direction. It exists in what's called a superposition, a state where it's simultaneously spinning in all possible directions at once. Your brain is probably rejecting this idea right now. How can something spin in all directions at once? Think of it like a coin spinning in the air. While it's spinning, it's neither heads nor tails. It's in a state of being both. But the moment it lands, it becomes one or the other. Quantum particles are similar, except they remain in this spinning state until something measures them. Now here's where entanglement gets absolutely mind-bending. When you create two entangled photons from that crystal, their spins become correlated in a very specific way. If you set up your experiment correctly, the rule becomes, if one photon has spin up, the other must have spin down. But remember, neither photon has a definite spin until you measure it. So before measurement, both photons are simultaneously spin up and spin down. They're in a superposition. The moment you measure one photon and find it spin up, the other photon, no matter where it is in the universe, instantly becomes spin down. Not probably spin down. Not eventually spin down. Instantly spin down. And this has been measured with particles separated by distances of over 1,200 kilometers, or about 745 miles, in experiments conducted by Anton Zeilinger's team in 2017. The correlation happens so fast that if there were any signal traveling between the particles, it would have to be traveling at least 10,000 times faster than the speed of light. But here's what will truly melt your brain. The particles don't know what their spin is until you measure one of them. The moment you measure particle A and find it spin up, particle B doesn't just happen to also be spin down, like it was all along, and we just didn't know it. No, particle B, WAs, in a superposition of both spin up and spin down until the instant you measured particle A. Your measurement of particle A somehow reaches across the void and forces particle B to choose a definite state. This is what Einstein found so disturbing that he rejected it entirely. He believed in what's called local realism. Local means that objects are only influenced by their immediate surroundings, and reality means that objects have definite properties, whether or not we observe them. A tree falling in a forest makes a sound whether anyone is there to hear it. But quantum entanglement violates local realism in the most profound way possible. Let me give you an analogy that captures how strange this really is. Think of two magic boxes, one in New York and one in Tokyo. Each box contains a light bulb that can be either red or green. Before you open either box, the light bulbs are both red and green simultaneously. They're in a superposition. The moment you open the box in New York and see a red light, the box in Tokyo instantly, faster than any signal could travel between the cities, contains a green light. Not only that, but the Tokyo light wasn't green before you opened the New York box. It became green the instant you looked at the red light. The active observation in New York reaches across the Pacific Ocean and changes the physical state of the Tokyo box. This is not science fiction. This is experimentally verified reality. And here's the kicker that should be keeping you up at night. If this is how the universe actually works at the quantum level, and everything in the universe is made of quantum particles, then what does this say about the nature of reality itself? Albert Einstein was arguably the greatest physicist who ever lived. He gave us relativity, E equals mc. He revolutionized our understanding of space, time, gravity, and energy. And yet, quantum entanglement bothered him so much that he devoted decades trying to prove it couldn't exist. Let me explain why this phenomenon was Einstein's personal nightmare. Einstein's entire worldview was built on a concept called determinism and locality. Determinism means that if you know the present state of a system and the laws of physics, you can predict its future and retrodict its past with perfect accuracy. The universe operates like an incredibly complex clock. Everything that happens is the inevitable result of what came before. Locality means that an object is only directly influenced by its immediate surroundings. For something far away to affect something here, a signal must travel between them, and that signal cannot travel faster than light. Quantum mechanics, and especially quantum entanglement, obliterates both of these principles. In 1927, at the Fifth Solvay Conference in Brussels, the greatest physicists of the era gathered to debate the implications of quantum mechanics. Einstein famously declared, "God does not play dice with the universe." He was objecting to the fundamental randomness built into quantum mechanics. According to quantum theory, when you measure a particle in superposition, the outcome is genuinely random. It's not that we lack information to predict the result. The result is fundamentally unpredictable until the moment of measurement. Niels Bohr, the Danish physicist who was the main architect of the Copenhagen interpretation of quantum mechanics, shot back at Einstein, "Stop telling God what to do." This exchange represents one of the greatest intellectual debates in human history. Was Einstein right that quantum mechanics was incomplete, that there must be hidden variables we haven't discovered yet that determine the outcomes? Or was Bohr right that the universe is fundamentally probabilistic and that observation plays a crucial role in creating reality? This brings us back to 1935 and the EPR paradox. Einstein, Podolsky, and Rosen constructed a thought experiment that was supposed to expose the absurdity of quantum mechanics. Here's the logic. If quantum mechanics is correct, then measuring one particle instantly affects another particle far away. But this would require faster-than-light communication, which violates relativity. Therefore, quantum mechanics must be incomplete. There must be hidden variables that determine each particle's properties in advance. The particles aren't really in superposition. They have definite properties all along, and we just don't know what they are until we measure them. Think of it like this. Imagine someone puts a red marble in one box and a blue marble in another, then scrambles the boxes so you don't know which is which. When you open one box and find a red marble, you instantly know the other box contains a blue marble. But nothing spooky happened. The marbles had their colors all along. You just gained information about them. Einstein believed quantum particles worked the same way. For 3 decades, this remained a philosophical debate because nobody knew how to test it experimentally. Then John Bell changed everything. In 1964, Bell proved mathematically that if Einstein's hidden variables existed, measurements on entangled particles would have to obey certain statistical constraints, now known as Bell inequalities. But if particles were truly in superposition and truly entangled as quantum mechanics claimed, they would violate these inequalities in specific measurable ways. Here's an analogy to understand Bell's inequality. Imagine you have 2 friends, Alice and Bob, who each get asked random yes or no questions. If they're coordinating their answers ahead of time using a predetermined strategy, their answers will match in certain predictable patterns, no matter how clever their strategy is. But if they're somehow telepathically connected, sharing one mind, their answers could match in ways that break the patterns that any predetermined strategy could produce. Bell figured out the exact mathematical test to distinguish between these scenarios. In the 1970s, a young French physicist named Alain Aspect decided to actually perform this test. Between 1980 and 1982, Aspect and his team at the Institute of Optics in Paris conducted a series of experiments with entangled photons. They measured the polarization of these photons, which is another quantum property similar to spin. The experiments had to be incredibly precise because they needed to ensure that the measurements on the 2 photons were made so quickly and so far apart that no signal traveling at the speed of light could have time to pass between them. What did they find? Reality violated Bell's inequalities. Einstein's hidden variables didn't exist. The universe failed Einstein's test. Think about what this means. There is no predetermined script for the universe. These particles genuinely don't have definite properties until they're measured. And when you measure one, something non-local, something that transcends space, instantly affects the other. But 400 meters wasn't enough for some skeptics. So scientists went bigger. In 2017, a Chinese team led by Jianwei Pan conducted an experiment using the Mises satellite, the world's first quantum communications satellite. They created entangled photons on the satellite and sent one photon to a ground station in Delingha and another to a ground station in Lijiang, separated by 1,203 kilometers, or about 747 miles. The measurements occurred simultaneously, with the photons being measured within microseconds of each other. A light signal would have needed 4 milliseconds to travel between the stations. The correlation still occurred instantly, violating Bell's inequality with unprecedented precision. Think about this. These particles, separated by over 1,200 kilometers, with a mountain range between them, maintained their spooky connection. Something about them is connected in a way that transcends physical space. The detection loophole is more subtle, but equally important. The issue is that photon detectors aren't perfect. They only detect a small fraction of the photons sent to them. Could it be that the particles are only appearing entangled because we're only detecting a biased sample of them? To close this loophole, you need detectors that are efficient enough to catch most of the particles. In 2015, multiple teams, including one led by Ronald Hansen at Delft University of Technology in the Netherlands, conducted loophole-free Bell tests using not photons, but electron spins and diamonds. These experiments had high enough detection efficiency to rule out any possible bias. the entanglement remained. The freedom of choice loophole is perhaps the most philosophically disturbing. It asks, how do we know that the random choices we make about what measurements to perform aren't somehow predetermined by the same hidden variables that might be controlling the particles? Maybe the universe conspired at the Big Bang to create correlations between the particles and the settings of our measurement devices. This sounds paranoid, but in science, you have to rule out every possibility, no matter how unlikely. To close this loophole, scientists needed to ensure that the choice of what to measure was truly random and truly independent of the particles' past. In 2016, a global collaboration called the Big Bell Test recruited 100,000 volunteers from around the world to play video games. The human choices made during these games were used to determine the measurement settings in multiple Bell test experiments occurring simultaneously around the globe. The idea was that human free will, assuming it exists, would generate truly random and unpredictable choices that couldn't possibly have been correlated with the particles billions of years ago. The result? Entanglement survived even this test. But scientists took it even further. In 2018, researchers used light from distant quasars, astronomical objects billions of light years away, to determine the measurement settings. The light from these quasars was emitted billions of years ago, long before the entangled particles in the experiment were even created. If there were hidden variables coordinating everything, they would have had to be set in motion at the very beginning of the universe, with the Big Bang itself orchestrating this cosmic conspiracy. The experiment still showed entanglement. What's the conclusion? Either quantum entanglement is real, or the universe is engaged in a conspiracy so elaborate that it coordinated events across billions of years and billions of light years just to fool our experiments. Occam's razor, the principle that the simplest explanation is usually correct, strongly suggests that entanglement is simply real. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their groundbreaking experimental work on entanglement. The Nobel Committee's announcement included this remarkable statement: "These experiments have laid the foundation for a new era of quantum technology and established the violation of Bell inequalities." In other words, the scientific establishment officially declared, the universe is not local. Reality is far stranger than Einstein imagined. Now we need to confront what entanglement actually means for the nature of reality itself. And I'm warning you, this section is going to fundamentally challenge everything you think you know about existence. Let's start with a simple question. What is real? Before quantum mechanics, the answer seemed obvious. Real things have definite properties independent of observation. A chair is in your room whether you're looking at it or not. The moon is in the sky whether anyone is observing it or not. Einstein famously asked, "Do you really believe that the moon isn't there when nobody looks?" He was expressing his conviction that reality exists independently of observation. But quantum entanglement, combined with the broader framework of quantum mechanics, suggests that Einstein's intuition might be wrong. When two particles are entangled, neither has definite properties until one is measured. The act of measurement doesn't just reveal a pre-existing property. It seems to create that property. And the measurement of one particle somehow instantaneously influences the other, no matter the distance between them. This leads us to several possible interpretations of reality, each more mind-bending than the last. Let's explore them. The first interpretation is the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. This interpretation says that quantum particles don't have definite properties until they're measured. The act of measurement collapses the wave function, forcing the particle to choose a definite state from the superposition of possible states. But the Copenhagen interpretation doesn't really explain how measurement causes this collapse, or it makes a measurement special. It essentially says, this is just how the universe works. Stop asking why. Think of the Copenhagen interpretation like this. Reality is like a game of quantum roulette, where the ball is simultaneously on all numbers until someone looks at the wheel, and only then does it land on a specific number. The very act of observation creates the outcome. The second interpretation is the many worlds interpretation, first proposed by Hugh Everett in 1957. This interpretation takes the mathematics of quantum mechanics completely seriously and arrives at a shocking conclusion. The wave function never collapses. When you measure a particle in superposition, the universe splits into multiple branches. In one branch, you measure spin up. In another branch, you measure spin down. Both outcomes happen. They just happen in different parallel realities. Every quantum measurement creates a branching of reality into parallel universes. Let that sink in. According to many worlds, every time you measure an entangled particle, the universe branches into versions where the particle has different properties, and each version of you sees a different outcome. There's a version of you in another branch of reality who measured the opposite result. Entanglement still looks spooky in this interpretation because the branches remain correlated. If in this branch you measured spin up, then in this branch, the distant entangled particle must be spin down, and this correlation exists across all branches. Think of many worlds like this. Reality is like an infinitely branching tree, where every quantum event creates new branches, and you're traveling down one particular branch, while countless other versions of you travel down other branches, all equally real. The third interpretation is called pilot wave theory, or de Broglie-Bohm theory, proposed by Louis de Broglie in the 1920s and developed by David Bohm in the 1950s. Interpretation tries to restore determinism by proposing that particles do have definite positions and properties at all times, but they're guided by a pilot wave that fills all of space. This wave is non-local, meaning it can instantly connect distant particles. In this view, entanglement happens because the pilot wave is an instantaneous connection across space. Think of pilot wave theory like this. Particles are like surfers riding a cosmic wave that spans the entire universe. And this wave can coordinate the motion of surfers on opposite sides of the ocean instantaneously. But here's the interpretation that's been gaining traction in recent years and might be the most profound. Relational quantum mechanics, developed by Carlo Rovelli in the 1990s. This interpretation suggests that properties like spin or position aren't absolute facts about particles. Instead, they're relative to the observer. A particle might have spin up relative to one observer and spin down relative to another, and both are equally valid descriptions of reality. In this view, there is no objective, observer-independent reality. Reality is always relative to some reference frame, some observer. Think of this like navigating. North isn't an absolute direction in the universe. It's defined relative to Earth's magnetic field. According to relational quantum mechanics, spin up and spin down aren't absolute properties. They're defined relative to the observer making the measurement. But wait, there's one more interpretation that's truly radical. Quantum Bayesianism, or cubism, developed by Carlton Caves, Christopher Fuchs, and Rudiger Schack. Cubism proposes that quantum mechanics isn't describing an external reality at all. Instead, it's a tool for calculating the probabilities of our personal experiences. The wave function isn't a real physical thing. It's a representation of our knowledge and beliefs about what we might experience. In this view, entanglement is about the correlation of our experiences, not about a spooky connection between particles. Think of cubism like this. Physics isn't describing what the world is. It's describing what we should expect to experience. A map is not the territory. Quantum mechanics is the map, and the territory might be fundamentally unknowable. So which interpretation is correct? Here's the honest answer. We don't know. All of these interpretations make the same predictions for any experiment we can actually perform. They're empirically equivalent. The choice between them is currently a matter of philosophical preference, not experimental data. But here's what we know for certain. At least one of our fundamental assumptions about reality is wrong. Either locality is wrong, and things can be instantaneously connected across space, or realism is wrong, and particles don't have definite properties until they're measured, or both are wrong. There is no way to maintain the classical view that reality is made of separate objects with definite properties that only interact locally. The universe is not what it seems. Space might be an illusion. Separateness might be an illusion. The solid, definite, local reality you perceive is a convenient fiction generated by your brain to help you survive. But it's not the deep truth of existence. At the quantum level, everything is connected to everything else in ways that transcend space and time. Now let's talk about how scientists are actually using quantum entanglement to build technologies that would have been considered pure science fiction just decades ago. Because here's the thing. Quantum entanglement isn't just a philosophical curiosity or a weird quirk of nature. It's a resource that can be harnessed to do things that are impossible with classical physics. The first and most developed application is quantum cryptography, specifically something called quantum key distribution. Here's the problem it solves. In our digital age, secure communication is crucial. When you send your credit card information to Amazon or your bank, you want to be sure that no one is eavesdropping. Classical encryption relies on mathematical problems that are hard to solve, like factoring large numbers. But hard doesn't mean impossible. It just means it would take classical computers an impractically long time to crack the code. However, a sufficiently powerful quantum computer could crack these codes relatively easily, which we'll get to later. Quantum cryptography offers something better, provably unbreakable security based on the laws of physics, not the difficulty of mathematical problems. Here's how it works. Alice wants to send a secret message to Bob. First, they need to share a secret key, a random string of bits that they'll use to encrypt and decrypt the message. Using quantum entanglement or quantum superposition, Alice can send quantum particles to Bob, encoding the key in their quantum states. Here's the beautiful part. If an eavesdropper, call her Eve, tries to intercept and measure these quantum particles to learn the key, she inevitably disturbs them because of the measurement problem we discussed earlier. When you measure a quantum system, you change it. Alice and Bob can detect this disturbance by comparing a subset of their key bits. If there's too much disagreement, they know someone was eavesdropping and they discard that key and try again. Think of it like this. Imagine sending a message written in ice. If anyone tries to read it along the way, the ice melts and you know someone looked at it. Quantum particles are even better because the laws of physics guarantee that eavesdropping is always detectable. This isn't theoretical. Quantum key distribution systems are already commercially available. In 2016, China launched the MISHIS satellite specifically for quantum communication experiments. By 2017, they had successfully established quantum encrypted communication between Beijing and Vienna, over 7,500 kilometers apart. The Chinese government now uses quantum cryptography to secure communications between banks in several cities. As quantum computers become more powerful and threaten to break classical encryption, quantum cryptography will become increasingly crucial for maintaining secure communications. The second major application is quantum computing, and this is where entanglement becomes truly powerful. Classical computers process information using bits, which can be either 0 or 1. Quantum computers use quantum bits, or qubits, which can be in superposition, simultaneously 0 and 1. But here's where it gets really interesting. When you entangle multiple qubits, you create quantum correlations between them that allow the quantum computer to explore many possible solutions to a problem simultaneously. Here's an analogy. Imagine you're trying to find the exit in a massive maze. A classical computer would try one path at a time, methodically checking each route. If there are a million possible paths, it might take a million steps. But a quantum computer with entangled qubits can explore many paths simultaneously through superposition and entanglement. The qubits represent different paths, and through quantum interference, the wrong paths cancel out while the correct path is amplified. The quantum computer can solve the maze in a fraction of the time. In 1994, mathematician Peter Shor discovered an algorithm showing that a quantum computer could factor large numbers exponentially faster than any known classical algorithm. This was a bombshell because factoring large numbers is the basis for RSA encryption, the system securing most internet communications. A sufficiently large quantum computer could break RSA encryption, rendering much of our current digital security obsolete. In 2019, Google announced that their quantum computer, Sycamore, had achieved quantum supremacy. This was first demonstrated experimentally in 1997 by Anton Zellinger's team, teleporting the quantum state of a photon across a laboratory. By 2017, Chinese scientists using the Michis satellite teleported quantum states from the ground to a satellite 1,400 kilometers above Earth. This technology could be crucial for quantum communication networks and distributed quantum computing. But here's what's truly mind-blowing about all these applications. They're not exploiting some obscure detail of quantum mechanics. They're harnessing the same spooky non-locality that disturbed Einstein. The very feature of reality that seems most impossible, the instantaneous connection between distant particles, is becoming the foundation for revolutionary technologies. Now we need to address the elephant in the room, the question that's probably been nagging at you since the beginning. What does quantum entanglement have to do with consciousness? This is where we venture into controversial territory, where hard science meets speculation, but it's a question we can't ignore because the implications are too profound. Let's start with the measurement problem. We've discussed how measuring a quantum system collapses its wave function, forcing it from a superposition into a definite state. But what constitutes a measurement? Does it require a conscious observer? This question has haunted quantum mechanics since its inception. In the famous Schrödinger's cat thought experiment from 1935, a cat is placed in a sealed box with a quantum device that has a 50% chance of killing the cat. According to quantum mechanics, until someone opens the box and observes the cat, it exists in a superposition of being both alive and dead simultaneously. But this seems absurd. Surely the cat itself knows whether it's alive or dead, right? Does consciousness play a role in collapsing the wave function? Some physicists, most notably Eugene Wigner, a Nobel Prize winner, argued that consciousness must play a fundamental role in quantum mechanics. Wigner proposed in the 1960s that consciousness is what collapses the wave function. In his view, the Schrödinger's cat remains in superposition until a conscious being observes it, because consciousness is the special ingredient that transforms quantum possibilities into classical reality. But here's where it gets truly strange. If consciousness collapses wave functions, and wave functions exist in superposition across space, and entangled particles are connected non-locally, could consciousness itself be non-local? Could consciousness be the thing that's actually entangled across space and time? Let me be crystal clear. Most physicists today reject the idea that consciousness is necessary for wave function collapse. Modern interpretations, like decoherence theory, explain that wave function collapse isn't a special event at all. Instead, quantum systems become entangled with their environment, which includes measurement devices, air molecules, and everything else. And this entanglement causes the system to behave classically without any need for consciousness. The quantum superposition doesn't disappear. It just spreads out into the environment in a way that makes it undetectable. But here's what we can't ignore: the hard problem of consciousness. The question of why and how physical processes in the brain give rise to subjective experience remains completely unsolved. We have no scientific explanation for why there's something it's like to be you, why the electrochemical signals in your brain produce the vivid subjective experience of being conscious. Some researchers, most notably the physicist Roger Penrose and the anesthesiologist Stuart Hameroff, have proposed that quantum processes in the brain might be crucial for consciousness. Their theory, called orchestrated objective reduction, or ORCO-R, suggests that quantum computations occur in structures called microtubules inside neurons. These microtubules might maintain quantum coherence, including entanglement, for brief periods, and consciousness might emerge from these quantum processes. Think of this theory like this. Your brain isn't just a classical computer made of neurons firing electrically. It's a quantum computer with quantum processes occurring at the molecular level inside your neurons. And consciousness emerges from these quantum computations in ways that classical computing cannot explain. Most neuroscientists are skeptical of this idea because the brain is a warm, wet, noisy environment, and quantum coherence is extremely fragile. It seems impossible for delicate quantum states to survive long enough in the brain to do anything useful. However, recent research has found surprising examples of quantum effects in biological systems. In 2007, researchers discovered quantum coherence in photosynthesis. Plants use quantum superposition and possibly entanglement to transfer energy with remarkable efficiency during photosynthesis. In 2014, scientists found evidence of quantum effects in bird navigation. European robins apparently use quantum entanglement in molecules in their eyes to sense Earth's magnetic field. If evolution has harnessed quantum effects for photosynthesis and navigation, could it have also harnessed them for consciousness? Here's what we know for certain. Consciousness and quantum mechanics are the two biggest mysteries in science, and both violate our common sense intuitions about reality. Consciousness seems to be irreducible to purely physical processes, and quantum mechanics seems to show that reality depends on observation in some way. The connection between them might be coincidental, or it might point to something profound about the nature of existence. But let me take you down an even stranger rabbit hole. What if consciousness isn't produced by the brain at all? What if consciousness is a fundamental feature of the universe, like space and time and energy, and the brain is just a receiver or a filter that tunes into it? This idea, called panpsychism, suggests that consciousness is everywhere, in everything, at every scale. Electrons have some tiny amount of consciousness. Rocks have some tiny amount of consciousness. And complex systems like brains have a lot of consciousness because they integrate vast amounts of information. If consciousness is fundamental and non-local, then quantum entanglement might be the mechanism by which consciousness binds together different parts of the universe. When particles become entangled, maybe they're sharing consciousness in some sense. This would explain the measurement problem. Consciousness doesn't collapse the wave function. Consciousness is the wave function. Or at least, consciousness is what the wave function describes. Now, I need to be completely honest with you. Everything I've said in the last few paragraphs is highly speculative. It's not established science. It's philosophy informed by physics. But here's why it matters. Quantum entanglement has proven that our intuitive understanding of reality is wrong. Space might be an illusion. Separateness might be an illusion. If we're wrong about something as fundamental as whether distant objects are truly separate, maybe we're also wrong about consciousness. Think about your own experience of consciousness right now. You feel like a unified self, a single you, having a continuous stream of experiences. But your brain is made of roughly 86 billion neurons, each one a separate physical entity doing its own thing. Somehow, these separate neurons create a unified consciousness. How? This is called the binding problem in neuroscience, and we have no good answer. But here's the truly mind-bending possibility. If quantum entanglement can make spatially separated particles behave as a single, unified system, could quantum entanglement in the brain be what binds separate neurons into a unified conscious experience? Could the strange, non-local connections of entanglement be the same kind of connection that makes you feel like a unified self rather than 86 billion separate cells? And here's where we go even deeper. If entangled particles form a single system regardless of distance, and everything in the universe was entangled at the Big Bang when everything was in the same place, then maybe at some deep level, everything in the universe is still entangled. Maybe you and I, and the stars, and everything that exists are all part of one vast, universal quantum system. Maybe the separateness we experience is the illusion, and the deep truth is that we're all aspects of one unified consciousness experiencing itself from different perspectives. This idea appears in many mystical and spiritual traditions. The Hindus call it Brahman, the ultimate reality underlying all existence. The Buddhists describe it as the interconnectedness of all things. Quantum entanglement might be the universe showing us, through the cold, hard language of mathematics and experiment, that these ancient intuitions were pointing towards something true. Now, before you think I've completely lost it, let me reiterate. This is speculation. We don't know if consciousness has anything to do with quantum mechanics. We don't know if quantum processes are important in the brain. We don't know if panpsychism is true. But what we do know is that quantum entanglement has revealed that reality is far stranger than we imagined. And when reality is that strange, we should be humble about what might be possible. Let's dive into some of the most brain-melting paradoxes and thought experiments that arise from quantum entanglement, because this is where the true weirdness becomes undeniable. We've already discussed the EPR paradox and Schrodinger's cat, but there are other scenarios that push our understanding to the breaking point. First, let's talk about the delayed choice quantum eraser experiment, first performed by Yoon-Ho Kim and his colleagues in 1999. This experiment shows that what you choose to measure in the future can apparently affect what happened in the past. Let me explain how this works and prepare for your brain to hurt. You start with a source that produces entangled photon pairs. Let's call them photon A, and photon A goes through a double-slit apparatus. That famous experiment showing wave-particle duality. If you don't measure which slit photon A goes through, it behaves like a wave and creates an interference pattern. If you do measure which slit it goes through, it behaves like a particle and no interference pattern appears. This much is standard quantum mechanics. But here's the twist. Photon B, the entangled partner, goes on a different path to a detection system. Because the photons are entangled, photon B carries information about which path photon A took. Now, you can choose to measure this which path information from photon B, or you can erase it by running photon B through another apparatus that scrambles the information. Here's the mind-blowing part. You can delay this choice until after photon A has already hit its detector. If you choose to measure the which path information, photon A will have behaved like a particle with no interference pattern. If you choose to erase the which path information, photon A will have behaved like a wave with an interference pattern. Your future choice appears to retroactively determine what happened to photon A in the past. Think about this. Photon A hits its detector at time t plus 1. You make a choice about what to do with photon B. But when you look at the data, photon A's behavior at time t was consistent with the choice you made at time t plus 1. It's as if your future decision reached back in time and changed the past. Now, before you start planning time travel paradoxes, there's a crucial detail. You can't see the pattern in photon A's data until you know what happened with photon B. You have to correlate the results. So you can't use this to send information to the past. Nevertheless, the implication is staggering. The timeline of cause and effect in quantum mechanics is not what we thought it was. The future can influence the past in some sense. One interpretation is that the past doesn't become definite until the future measurement is made. Until you choose what to measure with photon B, both possibilities, photon A behaving like a wave and like a particle, exist in superposition. Your measurement of photon B collapses not just the present state, but retroactively collapses the past state of photon. A time itself might be a quantum phenomenon subject to superposition. Here's another paradox: the quantum bomb tester, also called the Elitzur-Vaidman bomb tester, proposed by Avshalom Elitzur and Lev Vaidman in 1993. Imagine you have a bomb that will explode if even a single photon hits its trigger. The bomb is ultra-sensitive. How can you test whether the bomb is functional without exploding it? Classically, this seems impossible. If you send a photon to test it and the bomb is functional, it explodes. But if the bomb is broken, nothing happens. Either way, if you want to know if a functional bomb is present, it has to explode, right? Wrong. Using quantum superposition and the mere possibility of measurement, you can determine with certainty that a functional bomb is present without ever triggering it. Here's how. You send a single photon through a beam splitter that puts it in superposition, traveling down two paths simultaneously. One path goes past the bomb trigger. The other path doesn't. These paths then recombine at another beam splitter and lead to two detectors. If there's no bomb, the photon is in superposition on both paths, and when the paths recombine, quantum interference ensures the photon always goes to detector 1, never detector 2. But if there's a functional bomb in one path, the mere possibility that the photon could hit the trigger and be measured causes the photon's wave function to partially collapse. About 25% of the time, the photon actually takes the path toward the bomb and explodes it. But another 25% of the time, the photon takes the other path, yet detector 2 clicks instead of detector 1. When detector 2 clicks, you know with certainty that there's a functional bomb present, even though the photon never interacted with it. You learned about the bomb's presence through the negative result, by the photon not being on that path. This is called interaction-free measurement, and it's been experimentally verified. You can gain information about something without ever physically interacting with it. Think about how bizarre this is. The universe allowed you to learn about the bomb's existence because the photon could have interacted with it. The mere potential for interaction was enough. It's like learning that a dangerous dog is behind a door because you noticed that your coin flip, which was going to determine whether you opened the door, suddenly started behaving differently. Reality responds to possibilities, not just actualities. Now let's discuss the quantum Cheshire cat, an experiment performed in 2013 by Tobias Denkmeyer and colleagues. The Cheshire cat from Alice in Wonderland can separate its grin from its body. The quantum version shows that you can separate a particle from its properties. Using neutrons, researchers created a situation where the neutrons traveled down one path, but their magnetic spin traveled down a different path. The particle and its property were spatially separated. How is this even possible? In quantum mechanics, properties like spin are not intrinsically attached to particles. They're contextual and can be manipulated separately through clever experimental design. This gets at something profound. In quantum mechanics, particles don't have properties the way classical objects do. A baseball has the property of being round even when no one is looking at it. But a quantum particle's properties are more like relationships between the particle and the measuring device. The property doesn't exist independently of the context of measurement. Here's one final thought experiment that will haunt you: the Wigner's friend paradox, an extension of Spinger's cat proposed by Eugene Wigner. Imagine Wigner's friend is in a sealed laboratory measuring a quantum system. From the friend's perspective, the measurement happens, the wave function collapses, and the system has a definite state. But from Wigner's perspective outside the lab, the friend and the quantum system together are isolated from the outside world and remain in superposition. The friend is in a superposition of having measured different results. So who's right? Did the wave function collapse when the friend made the measurement? Or does it remain in superposition until Wigner opens the lab? Both the friend and Wigner are observers using quantum mechanics, so both should be able to apply the theory. But they give contradictory descriptions of reality. The friend says the measurement happened and the system has a definite state. Wigner says the measurement hasn't happened yet from his perspective. In 2019, researchers at Heriot-Watt University in Scotland performed a version of this experiment and confirmed the paradox is real. Two observers can have irreconcilable accounts of the same event. This suggests that there is no single objective reality that all observers agree on. Reality itself might be observer-dependent. Think about what this means for your life. Right now, you believe you're having certain experiences, making certain observations. From your perspective, the wave function of your environment has collapsed. You see definite things. But from the perspective of someone outside your system, you and your entire environment might still be in quantum superposition. There might not be a fact of the matter about what you're experiencing until someone measures you from the outside. This is not science fiction. This is what the mathematics and the experiments are telling us. Reality is observer-dependent. There is no view from nowhere, no God's eye view of an objective reality that all observers share. The result? Photons 2 and 4 showed correlations identical to what you'd see if they were entangled, even though photon 2 was created, and its partner was measured before photon 4 even existed. The entanglement seemed to jump across time, connecting photons through the measurements of their now destroyed partners. Photon 1 and photon 3, which never coexisted, acted as a bridge connecting photons 2 and 4 across time. Think about what this means. Entanglement isn't just a spatial connection. It's a connection that can exist across the dimension of time. A particle in the present can be entangled with a particle that will exist in the future or that existed in the past. The particle in the future doesn't even need to exist yet for this connection to be real. This leads to a radical reconceptualization of time itself. We typically think of time as a flowing river, with the past fixed, the present fleeting, and the future yet to be determined. But quantum mechanics, and especially temporal entanglement, suggests that this view is wrong. Instead, time might be more like space, a dimension in which all moments exist simultaneously from some outside perspective, and the flow of time is an illusion created by our conscious experience. This is actually consistent with Einstein's theory of relativity, which describes space-time as a four-dimensional block where past, present, and future all coexist. Einstein himself wrote in a letter to the family of his deceased friend, Michel Bessot, "For we convinced physicists, the distinction between past, present, and future is only an illusion, however persistent." He was describing the block universe view, where time doesn't flow. We simply have different perspectives on different slices of the four-dimensional space-time block. Temporal entanglement takes this further. If particles can be entangled across time, then the block universe isn't just a static structure. It's a quantum structure where different times are connected through entanglement. Cause and effect become murky. An event in the future can be correlated with an event in the past, not because the future event caused the past event, or vice versa, but because they're both part of a larger, atemporal quantum system. Here's an analogy. Imagine watching a movie. From the perspective of the characters in the movie, time flows from beginning to end. Events in the present are caused by events in the past. But from your perspective, watching the film, all the frames exist simultaneously on the disc. The character's experience of cause and effect is real from their perspective inside the movie, but from outside, all moments coexist timelessly. Temporal entanglement suggests that reality might be like this movie, with all moments connected in a temporal structure. But here's where it gets truly strange. In 2016, physicist Lorenzo Macone proposed a thought experiment involving entanglement and time travel. If you could create a particle that's entangled with a past version of itself, you could potentially send quantum information to the past. Most physicists believe this is impossible because it would create causal paradoxes, like the famous grandfather paradox, where you go back in time and prevent your own birth. However, quantum mechanics might allow a way around this through the many worlds interpretation. If time travel creates a branching of realities, you could travel to the past of a different branch, avoiding paradoxes. Your measurements in the present would be correlated with measurements in the past of a parallel timeline. The mathematics of quantum mechanics doesn't forbid this. It just requires the universe to split into branches. Whether or not time travel is actually possible, temporal entanglement tells us something profound. The past might not be as fixed as we think. Measurements in the present can be correlated with measurements in the past in ways that seem to violate our normal understanding of causality. The past, present, and future might all be part of one entangled quantum system where time is just another dimension similar to space. Think about your own life. You think of your past as fixed, a series of events that happened and are now unchangeable. But from a quantum perspective, your past might still be in superposition until something in the present or future collapses it. The decisions you make now might be entangled with events in your past in ways that transcend normal causality. This is deeply unsettling. It suggests that we don't have a complete picture of what has already happened, let alone what will happen. The timeline you experience is just one perspective on a vastly more complex quantum structure. History might not be a linear sequence of fixed events, but a superposition of possibilities that are still being determined by future observations. Let's zoom out to the largest scales and explore what quantum entanglement means for the entire universe, because this is where the implications become truly cosmic. If entanglement is a fundamental feature of reality, it must have played a crucial role in the origin and evolution of the cosmos itself. Let's start at the very beginning, the Big Bang. About 13.8 billion years ago, the entire observable universe, everything that exists within the boundary of what we can see, was compressed into a region smaller than an atom. Everything was in the same place. In quantum mechanics, when particles are in the same place and interact, they become entangled. This means that at the moment of the Big Bang, everything in the universe became entangled with everything else. Now, the universe has expanded dramatically since then. The observable universe is now about 93 billion light years across. But here's the key question. When particles separate after becoming entangled, do they remain entangled forever? According to the mathematics of quantum mechanics, yes. Unless something actively disrupts the entanglement through a process called decoherence, entangled particles remain connected indefinitely, no matter how far apart they move. This leads to a staggering conclusion. Everything in the universe might still be entangled with everything else. You are quantum mechanically connected to the most distant galaxies. The atoms in your body are entangled with atoms on the other side of the cosmos. At the deepest level, the universe is not a collection of separate objects. It's one vast, entangled quantum system. This might sound like mystical nonsense, but it's actually taken seriously by physicists studying quantum cosmology. In fact, entanglement might solve one of the biggest mysteries in cosmology, the horizon problem. Here's the issue. When we look at the cosmic microwave background, the faint radiation left over from the Big Bang, we see that it has almost exactly the same temperature in all directions, about 2.7 Kelvin. The temperature varies by less than 1 part in 100,000 across the entire sky. But here's the problem. Regions of the sky that are on opposite sides from our perspective are so far apart that light hasn't had time to travel between them in the 13.8 billion years since the Big Bang. They've never been in causal contact. So how did they end up at the same temperature? It's like finding that two isolated communities on opposite sides of the Earth have identical cultures, languages, and technologies without ever communicating. The standard solution is cosmic inflation, The idea that the universe underwent a brief period of exponential expansion very early on, when it was a tiny fraction of a second old. This expansion was so rapid that regions that are now far apart were once close, enough to equilibrate to the same temperature before being blown apart. Inflation works well at explaining the observations. But here's an alternative, or perhaps complementary, explanation. What if the uniformity of the cosmic microwave background is due to quantum entanglement? If all regions of the universe are entangled, they're not truly separate, and their properties can be correlated instantaneously without any signal traveling between them. The universe appears uniform because it's fundamentally one entangled system, not a collection of separate, independent regions. Some physicists, including Juan Maldacena and Leonard Susskind, have proposed a radical idea. Entanglement and the geometry of spacetime might be deeply connected. There's a conjecture called A equals EPR, which links Einstein-Rosen bridges, also known as wormholes, with Einstein-Podolsky-Rosen entanglement. The idea is that when two particles are entangled, they're connected by a tiny wormhole in the fabric of spacetime itself. The particles aren't connected across space. They're connected through space, through a shortcut in the geometry. Think of spacetime like a bedsheet. Normally, to get from one point to another, you travel across the surface. But if you fold the sheet and poke a hole through it, you create a shortcut. According to A equals EPR, entanglement creates these shortcuts, these wormholes, connecting distant parts of the universe. Space itself emerges from the pattern of entanglement between quantum bits of information. This leads to an even more radical idea, proposed by physicist Mark van Ramsdonk and others. Space-time itself might be an emergent phenomenon arising from quantum entanglement. In this view, space is not fundamental. At the deepest level, there is no space, just quantum information and entanglement. Space emerges as an approximate description that works well at large scales, kind of like how water seems like a smooth liquid, even though it's actually made of discrete molecules. If this is true, then the question, how far apart are two entangled particles, doesn't even make sense at the fundamental level, because there is no space between them. They're directly connected through entanglement. And distance is just a convenient fiction that emerges when we look at the system from our macroscopic perspective. Let's think about what this means for the ultimate fate of the universe. One of the big questions in cosmology is whether the universe will continue expanding forever, growing colder and darker in what's called the heat death, or whether it will eventually collapse back on itself in a big crunch. But if the universe is fundamentally one entangled quantum system, perhaps neither of these fates fully captures what will happen. Some physicists speculate that the universe might be in a superposition of expanding and contracting. From our perspective inside the universe, we see expansion. But from some outside perspective, if such a thing exists, the universe might exist in a quantum superposition of multiple histories. The many worlds interpretation, taken to a cosmological scale, suggests that there are countless parallel universes, each experiencing different fates, all existing in superposition in the quantum multiverse. Here's another mind-bending implication. If everything was entangled at the Big Bang, and entanglement can persist across time, then perhaps the Big Bang itself is entangled with the ultimate fate of the universe. The beginning and the end might be quantum mechanically connected. The initial conditions of the universe might not be randomly determined. They might be correlated with the final state through a time-like entanglement that spans the entire history of the cosmos. This suggests that the universe is not just evolving in time from past to future. It's a self-consistent quantum system where the past and future are mutually determining each other through entanglement. The whole history of the universe, all 13.8 billion years of it, and whatever billions of years lie ahead, is one entangled quantum state. Think about your place in this cosmic picture. You are made of atoms forged in the cores of stars that died billions of years ago. Those atoms are entangled with other atoms scattered across the galaxy and beyond. Your very existence is connected to the fundamental structure of space-time itself. You are not a separate entity moving through an empty void. You are an intrinsic part of the entangled quantum tapestry of the universe. Now we need to confront the deepest philosophical questions raised by quantum entanglement, because this phenomenon doesn't just challenge our understanding of physics. It challenges our understanding of existence itself. Let's explore what entanglement means for free will, identity, causation, and the nature of reality. First, let's tackle free will. The question of whether we have free will, whether our choices are genuinely free or determined by prior causes, has been debated for millennia. Quantum mechanics adds a strange twist to this debate. At the quantum level, events are fundamentally random and unpredictable. When a particle in superposition is measured, the outcome is random, not determined by any prior state. This randomness is not due to our ignorance. It's intrinsic to reality. Some philosophers argue that this quantum randomness provides a foundation for free will. Our choices aren't determined by the past, they argue, because there's genuine quantum randomness in the brain. But here's the problem. Randomness isn't freedom. If your choices are random, you're not controlling them. They're just happening to you. Free will seems to require that your choices are both not determined by the past and not random. They have to be caused by you, by your conscious intentions. But what could that even mean? Entanglement complicates this further. If your brain states are entangled with events in your environment, and those events are entangled with the distant past and potentially the future, then your choices aren't arising purely from within you. They're part of a larger, non-local quantum system that spans space and time. Your decision to read this script, to keep watching, might be entangled with events that happened years ago, or that will happen years from now. The boundary between you and the universe is not as clear as it seems. Here's a thought experiment. Imagine scientists could measure the quantum state of your brain right now in perfect detail. According to quantum mechanics, your brain is in a superposition of many possible states until measured. When they measure it, your brain collapses into one definite state, and you have one definite set of thoughts and memories. But before the measurement, you existed in a superposition of having different thoughts and memories. So which thoughts and memories are really yours? All of them? None of them? Only the ones that get actualized through measurement? This leads to questions about personal identity. What makes you you? Typically, we think of ourselves as having a continuous identity over time. You're the same person you were yesterday and will be tomorrow. But if you're a quantum system in superposition, there might be many versions of you, existing simultaneously in different branches of the wave function. Which one is the real you? In the many worlds interpretation, every time a quantum measurement occurs in your brain, the universe branches and different versions of you experience different outcomes. There's a version of you who decided to stop watching this video 10 minutes ago. There's a version of you who never started watching. There are versions of you making every possible choice in every possible situation. Are all of these versions equally real? Are they all you? If so, then personal identity is not what we thought it was. You're not a single thread of consciousness moving through time. You're a branching tree of consciousness, constantly splitting into different versions of yourself, and each version believes itself to be the real you. The unity of the self is an illusion, a trick your consciousness plays on you by only being aware of one branch at a time. Now let's think about causation. We normally think of causation as temporal. Causes precede effects. A cause is B, which causes C, but entanglement shows that particles can be correlated without any causal signal passing between them. And temporal entanglement shows that correlations can exist across time in ways that don't respect the usual causal order. If event A in the present is correlated with event B in the past, which caused which? Neither caused the other in the normal sense. Let's turn to the nature of reality itself. Is reality objective, existing independently of observers, or is it in some sense created by observation? Quantum mechanics seems to suggest the latter. The wave function describes multiple possibilities, and measurement seems to select one actuality. But we've seen that different observers can have different, incompatible accounts of what happened, as in the Wigner's friend paradox. This leads to a position called quantum Bayesianism, or cubism, which we touched on earlier. Cubism says that the wave function is not a description of objective reality. It's a description of an observer's beliefs about what they will experience. Quantum mechanics is fundamentally about the relationship between observers and the world, not about the world in itself. Think about what this means. When you look at the world, you're not seeing an objective reality that exists independently of you. You're seeing a reality that's partially constructed by your act of observation. The moon isn't there when nobody looks, at least not in a definite state. It's in a superposition of possible states, and your observation collapses it into the state you see. But this raises a puzzle. If reality is observer-dependent, how do different observers manage to agree on what they see? When you and I both look at the moon, we see the same moon. How is that possible if each of us is collapsing the wave function according to our own observation? The answer might be entanglement. When you and I both observe the moon, we become entangled with the moon and with each other. Our observations are correlated because we're all part of one entangled quantum system. From a God's eye view outside the system, if such a view existed, the moon is still in superposition, and so are we. But from inside the system, from our correlated perspectives, we see the same collapsed state because our measurements are entangled. This suggests a kind of consensus reality, where reality emerges from the correlations between observers. Reality is not imposed from outside. It's negotiated through entanglement between all the observers and the observed system. You and I share a reality because we're entangled, not because there's an objective reality external to both of us. Here's the final, most disturbing implication. If entanglement is fundamental and space is emergent, then there might be no meaningful distinction between inside and outside, your consciousness. Experiencing the world from your perspective might not be located in space at all. It might be a property of your quantum state, and that quantum state is entangled with the quantum states of everything else. The boundary between your mind and the external world might be an artificial construct. When you think about you perceiving the world, you're actually one unified quantum system looking at itself from a particular vantage point. Subject and object, observer and observed, mind and matter. All these dualities might be convenient fictions that break down at the quantum level. There is no fundamental boundary between you and the universe, because at the deepest level, you are the universe, experiencing itself from a particular perspective. Now I want to address you directly and help you integrate what you've learned into your personal worldview. Because understanding quantum entanglement isn't just an intellectual exercise. It should fundamentally change how you see yourself and your place in the cosmos. Let's start with something personal. Right now, you're watching this video on a device made of atoms. Those atoms, billions upon billions of them, were formed in the nuclear furnaces of ancient stars. When those stars died in supernova explosions millions or billions of years ago, they scattered those atoms across space. Eventually, those atoms came together on Earth, were mined and processed and assembled into the device you're holding. And now they're part of your immediate experience. But here's what you probably haven't considered. Those atoms in your device are quantum mechanically entangled with atoms all over the universe. They carry quantum correlations from their formation in stellar cores, from their journey through interstellar space, from every interaction they've had. And at this moment, they're becoming entangled with the atoms in your hands, in your eyes, in your brain. You are becoming quantum mechanically connected to this information, to this moment, in a way that transcends the classical idea of just reading or watching something. Think about the people in your life. Your parents, your siblings, your friends, your partner, if you have one. You think of them as separate individuals, and in the classical world of everyday experience, they are. But at the quantum level, every interaction you've had with them has created entanglement between your particles and theirs. When you hug someone, photons bounce between your bodies, air molecules are exchanged, quantum correlations are formed. You carry traces of everyone you've ever touched, quantum information that links you to them across space and time. This is not metaphorical. This is literal physics. The atoms in your body have been part of countless other bodies throughout history. You contain atoms that were once part of dinosaurs, of ancient humans, of ocean creatures, of plants. And all those atoms carry entangled histories. You are a temporary configuration of matter that has existed in countless other configurations, and you will disperse back into the universe when you die, carrying the quantum information of your existence forward into future configurations. Does this make you feel small or large? Both, perhaps. Small because you're not a separate, autonomous entity, but a temporary pattern in an incomprehensibly vast quantum system. Large because that quantum system is all there is, and you're an integral part of it. You're not in the universe. You are the universe, looking at itself through the particular lens of your consciousness. Now let's talk about your choices and your future. You probably think of your future as undetermined, a blank slate that you'll fill in through your decisions. But quantum mechanics suggests something stranger. Your future might already exist in superposition, with you simultaneously making every possible choice. From your current perspective, you'll experience following one particular path. But there are other versions of you, just as real, experiencing other paths. What does this mean for how you should live? Some people find this terrifying. If there are versions of you making every possible choice, do your choices even matter? But I'd argue the opposite. Your choices matter intensely because they determine which branch of the wave function you experience. The other branches might exist, but you're not experiencing them. You're experiencing this branch, the one created by the specific sequence of choices and quantum measurements that led to this moment. Every decision you make, from the trivial to the profound, is a measurement that collapses possibilities and creates your specific timeline. You can't control which branches exist, but you can control which branch you experience. And that's what free will might really be. Not the ability to make choices that are neither determined nor random, but the ability to be the measuring device that collapses your own possibilities. Think about your regrets, the things you wish you'd done differently. In the many worlds interpretation, there are versions of you who made those other choices. They're living the lives you wish you'd lived, but you're not them. You're here, in this branch, with these experiences. The question is not whether you could have chosen differently. You did choose differently in other branches, but what you're going to do now, in this branch, going forward. Let's talk about death, because quantum mechanics has something profound to say about it. You're afraid of death, most likely. Most people are. Death means the end of your consciousness, the cessation of your experiences, the dissolution of your identity. But what if consciousness itself is quantum in nature? What if your consciousness is not produced by your brain, but is a fundamental feature of the quantum state that happens to be correlated with your brain's state? In that case, death might not be what you think it is. When your brain ceases functioning, the quantum information that constituted your consciousness doesn't disappear. Quantum information can't be destroyed. That's a fundamental principle called quantum unitarity. The information disperses, spreads out into the environment, becomes part of the vast entangled state of the universe. In some sense, you don't die. You dissolve back into the universal quantum field from which you emerged. Now, I'm not claiming that there's an afterlife in any traditional sense. I'm not saying your consciousness continues intact after death. But I am saying that the hard boundary between existence and non-existence, between being alive and being dead, might not be as sharp as we think. You are never a separate entity to begin with. You are always part of the universal quantum system. Death just makes that fact more obvious. Here's something that might bring you comfort, or might disturb you. I'm not sure which. If the many worlds interpretation is correct, there are branches of the wave function, where you don't die when you think you do. Every time you face a life-threatening situation, there are branches where you survive, and branches where you don't. From your subjective experience, you can only experience the branches where you survive, because in the branches where you die, there's no more you to experience anything. This leads to a strange conclusion called quantum immortality. From your first-person perspective, you might subjectively experience living forever, because you can only experience the branches where you continue to exist. Every time you face death, from your perspective, you'll always be the version of you who survived, no matter how improbable that survival was. Of course, from the third-person perspective of others, you will eventually die in their branches. But from your perspective, you might jump from increasingly improbable survival to increasingly improbable survival, possibly experiencing a very strange and unlikely long life. I don't know if quantum immortality is real. Most physicists are skeptical. But it's a logical consequence of taking the many worlds interpretation seriously and thinking about what it means for subjective experience. And it's worth contemplating because it forces you to think about the relationship between your consciousness and the quantum structure of reality. Let's talk about meaning and purpose. In a classical universe of separate objects governed by deterministic laws, it's easy to feel that life is meaningless. You're just a machine made of atoms, following the laws of physics, with no real freedom or significance. But quantum mechanics, and especially entanglement, paints a very different picture. You're not a machine. You're a conscious observer who collapses wave functions, whose measurements create reality from possibility. You're not separate from the universe. You're how the universe observes itself. Every time you make an observation, every time you make a choice, you're participating in the creation of reality. You're not just watching the universe unfold. You're an active participant in its unfolding. Does that give your life meaning? That's for you to decide. But at minimum, it should dissolve any sense that you're insignificant or powerless. You're a nexus point in the vast quantum network of reality, a location where the universe becomes conscious of itself and makes measurements that affect the whole. You matter because the structure of reality itself is built on observers like you making measurements. Here's my challenge to you. Live as if entanglement is real. What would that mean? It would mean recognizing that you're not truly separate from other people, from nature, from the cosmos. It would mean understanding that your actions don't just affect you through classical cause and effect, but ripple out through quantum correlations in ways you can't fully predict or control. It would mean treating every interaction as sacred, because every interaction creates entanglement, binds you more deeply into the fabric of reality. It would mean being humble about your knowledge, because you're not observing reality from outside. You're part of the quantum system you're trying to understand. It would mean embracing uncertainty, because at the quantum level, the future genuinely isn't determined. It would mean finding wonder in the mundane, because every atom in your body carries a quantum history that stretches back to the Big Bang and forward to the end of time. Now let's explore what's happening right now at the cutting edge of quantum entanglement research, because scientists are pushing the boundaries of this phenomenon in ways that would have seemed like pure fantasy just a decade ago. The future is being built on the strange foundation of quantum mechanics, and you need to know what's coming. First, let's talk about quantum networks. Scientists around the world are building the quantum internet, a global network where information is transmitted using entangled particles. China is leading the way. In 2016, they launched the MISHA satellite, and by 2017, they had demonstrated quantum communication between Beijing and Vienna, over 7,500 kilometers apart. The Chinese government has invested billions in quantum technology, building quantum communication networks connecting major cities. But it's not just China. In Europe, the Quantum Internet Alliance is developing quantum network infrastructure across multiple countries. In the United States, the Department of Energy announced plans in 2020 to build a national quantum internet. The goal is to create a communication network that's fundamentally unhackable because of the laws of quantum mechanics. Here's how it works. Instead of sending classical bits of information, you send qubits, quantum bits that can be in superposition. These qubits can be entangled with qubits at the receiving end. Any attempt to intercept or measure these qubits disturbs them, immediately alerting both parties to the presence of an eavesdropper. It's physically impossible to hack this system without being detected. But the quantum internet will do more than just provide secure communication. It will allow distributed quantum computing, where quantum computers in different locations work together on the same problem, their qubits entangled across space. It will enable quantum sensing networks that can detect gravitational waves, measure magnetic fields with unprecedented precision, or even detect the presence of objects hidden underground or underwater. Imagine a future where your phone is connected to the quantum internet. You could send messages with absolute security. You could perform computations by borrowing qubits from a quantum computer on the other side of the world. You could participate in quantum sensing experiments that map the curvature of space-time or search for dark matter. The quantum internet will transform information technology in ways we're only beginning to imagine. Second, let's talk about quantum computers. Right now, we're in the noisy intermediate scale quantum, or NISQ era. Quantum computers exist and can perform certain calculations, but they're small, error-prone, and limited in what they can do. The largest quantum computers have a few hundred qubits, but they're not fully error-corrected, so they make mistakes. But progress is rapid. In 2019, Google claimed quantum supremacy with a 53-qubit processor. In 2021, researchers at the University of Science and Technology of China demonstrated a photonic quantum computer with 76 photons, claiming it was 10 billion times faster than the best classical supercomputer for a specific task. In 2023, IBM unveiled a 433-qubit quantum processor called Osprey, the largest quantum processor ever built. The race is on to build larger, more stable quantum computers with error correction. Once we achieve fault-tolerant quantum computing, with thousands or millions of qubits working reliably, we'll be able to solve problems that are completely intractable for classical computers. We'll be able to simulate complex molecules exactly, revolutionizing drug discovery and materials science. We'll be able to optimize logistics networks, financial portfolios, and energy grids in ways that will transform entire industries. We'll be able to break current encryption systems, forcing a complete redesign of digital security. But here's what's truly exciting. We'll be able to simulate quantum systems themselves. Right now, we struggle to understand quantum entanglement because we can't simulate large entangled systems on classical computers. The computational resources required grow exponentially with the number of particles. But a quantum computer can naturally simulate quantum systems because it is a quantum system. We'll be able to explore the behavior of entangled particles in situations we can't create in the lab, testing the limits of quantum mechanics itself. Third, let's talk about quantum biology, one of the most controversial and exciting frontiers. We mentioned earlier that quantum effects have been found in photosynthesis and bird navigation, but researchers are finding quantum effects in more and more biological systems. There's evidence of quantum coherence in enzyme function in the sense of smell, possibly even in DNA mutation. Some researchers speculate that quantum effects might be crucial for consciousness itself, as we discussed with the Orkor theory. While this remains controversial, experiments are underway to test whether quantum coherence exists in microtubules in neurons. If it does, and if this coherence plays a functional role in brain processing, it would mean that consciousness is fundamentally quantum, not classical. Imagine the implications if this is true. It would mean that artificial intelligence, based on classical computers, could never truly replicate human consciousness because consciousness requires quantum processes. It would mean that understanding the brain requires understanding quantum mechanics, not just neuroscience. It would bridge the gap between physics and biology, between matter and mind, in a way that could transform both disciplines. Fourth, let's talk about quantum sensing and metrology. Entangled particles can be used to make measurements with precision beyond what's possible classically. This is already being commercialized. Companies are developing quantum sensors for medical imaging that can detect magnetic fields produced by the brain or heart with unprecedented sensitivity. These could diagnose conditions earlier and more accurately than current technology. Quantum sensors could detect underground structures, like archaeological ruins or military bunkers, without digging. They could map mineral deposits, guiding mining operations. They could detect submarines or stealth aircraft by measuring tiny distortions in gravitational or magnetic fields. The military applications are enormous, which is why governments are investing heavily in this technology. But there are peaceful applications too. Quantum sensors could detect underground water sources, helping communities in drought-stricken regions. They could monitor volcanic activity or earthquake precursors, providing early warning of natural disasters. They could detect pollutants or pathogens at concentrations far below what current sensors can detect. Fifth, let's talk about testing the foundations of quantum mechanics itself. Even after a century, quantum mechanics still has unsolved mysteries. The measurement problem remains. We still don't know exactly what happens during measurement or why it causes wave function collapse. We don't know which interpretation is correct. We don't fully understand the relationship between quantum mechanics and gravity. Experiments are underway to probe these questions. Researchers are creating ever larger quantum superpositions to see where the boundary is between the quantum and classical worlds. In 2019, a team created a superposition of a molecule containing 2,000 atoms, the largest quantum superposition ever. They're working on creating superpositions of viruses, of living cells, even of tiny mirrors. Where does quantum behavior stop and classical behavior begin? Other experiments are testing whether gravity affects quantum superposition. Some theories suggest that gravity might cause wave function collapse, providing a solution to the measurement problem. Experiments dropping entangled particles in gravitational fields or putting quantum systems near massive objects, trying to detect any such effect. Perhaps the most ambitious experiment is trying to entangle two macroscopic objects through their gravitational interaction. If successful, this would prove that gravity is quantum, not classical, settling a major debate in physics. It would also be a step toward a theory of quantum gravity, unifying quantum mechanics and general relativity, the holy grail of theoretical physics. Sixth, let's talk about quantum teleportation networks. Remember, quantum teleportation doesn't transport matter or energy. It transfers quantum information. But that's still incredibly useful. Scientists have successfully demonstrated quantum teleportation over increasing distances, across lab benches, across cities, from ground to satellites. The goal is to build quantum repeaters, devices that can extend quantum teleportation over arbitrary distances, despite the fragility of quantum states. Once we have quantum repeaters, we can teleport quantum information globally, enabling the quantum internet to function at intercontinental scales. But some researchers are dreaming bigger. Could we eventually teleport complex quantum states, like the complete quantum state of a molecule, or a living cell, or even a brain? This is purely speculative, and most physicists think it's impossible for practical reasons, even if not theoretically forbidden. But it's worth considering. If consciousness is quantum, and if we could perfectly scan and teleport the quantum state of a brain, would we be teleporting consciousness itself? The point is this: Quantum entanglement is not just a curiosity to be studied in labs. It's the foundation for technologies that will transform our world within your lifetime. The quantum revolution is happening now, and it will affect you whether you understand it or not. But by understanding it, by grasping the fundamental strangeness of quantum entanglement, you're better prepared for the future that's coming. Let's be honest about what we still don't understand, because even after a century of quantum mechanics and decades of research on entanglement, profound mysteries remain. These aren't just gaps in our knowledge that will be filled in by more experiments. They're fundamental questions about the nature of reality itself. First, we still don't understand the measurement problem. When and why does wave function collapse occur? Is collapse even real, or is it just apparent, with the wave function continuing to exist in a branching multiverse? The mathematics of quantum mechanics describes how wave functions evolve, but it doesn't tell us what makes a measurement special, or what collapses the wave function. Different interpretations give different answers. Copenhagen says collapse happens upon measurement, but doesn't explain what constitutes a measurement. Many Worlds says collapse never happens. The wave function always evolves smoothly, and observers just experience one branch. Pilot wave theory says there's no collapse because particles always have definite positions, with the wave just guiding them. Cubism says collapse is just an update to our knowledge, not a physical event. But here's the disturbing truth. We have no experimental way to distinguish between these interpretations. They all make the same predictions for any experiment we can actually perform. This means that the question of what's really happening during measurement might be fundamentally unanswerable by science. We're forced to choose based on philosophical preferences, not empirical evidence. Think about what this means. At the heart of our most successful scientific theory is a gaping hole. We don't know what measurement is or why it has the effects it does. We can use quantum mechanics to build computers and communication systems and sensors, but we don't truly understand what's happening at the most fundamental level. Second, we don't understand the relationship between quantum mechanics and consciousness. We know that measurement collapses wave functions. We know that consciousness involves observation. But is consciousness necessary for measurement? Or is it just correlated with measurement? Could a rock or a computer or a bacterium collapse wave functions? Or does it require a conscious observer? The Wigner's friend paradox suggests that consciousness might be special because different conscious observers can have incompatible descriptions of the same event. But we have no idea how consciousness could cause physical effects like wave function collapse. We have no mechanism, no theory that connects the subjective experience of being conscious with the objective mathematics of quantum mechanics. Some physicists, like Roger Penrose, believe consciousness is quantum, and that understanding consciousness requires a new physical theory, a theory of quantum gravity that will unify quantum mechanics and general relativity. Others, probably the majority, believe consciousness is irrelevant to quantum mechanics and that the measurement problem will be solved without reference to consciousness. But here's the honest truth. We don't know. The hard problem of consciousness remains unsolved. We don't know why physical processes in the brain give rise to subjective experience. And we don't know whether consciousness plays any special role in quantum mechanics. These might be related questions, or they might be completely separate. We simply don't know. Third, we don't understand how quantum mechanics and gravity fit together. General relativity, Einstein's theory of gravity, describes space-time as a smooth, continuous fabric that curves in response to mass and energy. Quantum mechanics describes reality as discrete and probabilistic, with particles existing in superposition. These two frameworks are both extraordinarily successful in their domains, but they're fundamentally incompatible. When you try to combine them, you get infinities and nonsensical results. We have no quantum theory of gravity, no way to describe what happens at the Planck scale, the incredibly tiny distance of about 10 to 35 meters, where both quantum effects and gravitational effects should be important. We don't know what space-time is made of at the deepest level. We don't know if space-time is continuous or discrete, fundamental or emergent. Entanglement might hold the key. The A=EPR conjecture, connecting entanglement with wormholes, suggests that space-time geometry emerges from quantum entanglement. If this is true, then solving the mystery of how space emerges from entanglement might give us the quantum theory of gravity we're looking for. But we're not there yet. String theory, loop quantum gravity, and other approaches have been pursued for decades without producing testable predictions or a complete theory. We're still fundamentally in the dark about how quantum mechanics and gravity fit together, and until we solve this, we can't claim to understand the deepest nature of reality. Fourth, we don't understand the role of time in quantum mechanics. Time appears in quantum mechanics differently than space. Space is unobservable. You can measure a particle's position, but time is a parameter. It's what evolves according to the Schrödinger equation. Why this asymmetry? Why does time seem to flow in one direction, from past to future, when the fundamental equations of quantum mechanics are time-symmetric? The arrow of time, the fact that entropy increases and causes run-to-4 effects, seems to be a thermodynamic phenomenon, not a fundamental one. But if time is just another dimension like space, as relativity suggests, why do we experience it so differently? Why does entanglement seem to respect the arrow of time, with correlations usually flowing from past to future, even though the mathematics allows for time-like entanglement in both directions? Some physicists believe that time is an illusion, that all moments exist timelessly in the block universe, and our experience of time flowing is just a feature of our consciousness. Others believe time is fundamental, and that the block universe view is wrong. But we have no consensus, no definitive answer. Fifth, we don't understand why quantum mechanics works. We have the equations, and they make incredibly accurate predictions. But why these equations? Why does nature operate according to the rules of quantum mechanics rather than some other set of rules? Is quantum mechanics fundamental, or is it an approximation to some deeper theory? There are hints that quantum mechanics might emerge from something more fundamental. Some researchers are exploring whether quantum mechanics emerges from information theoretic principles, whether nature is fundamentally made of quantum information in the particles, and fields are just ways that information is organized. Others are exploring whether quantum mechanics is a special case of a more general theory that allows for violations of quantum mechanics under certain extreme conditions. But these are speculations. The fact is, we don't know why quantum mechanics is the way it is. We've discovered the rules of the game, but we don't know why these are the rules, or whether there might be other rules operating at scales or in domains we haven't explored yet. Sixth, and perhaps most troubling, we don't understand what we even mean by understanding at this level. Throughout the history of science, to understand something meant to explain it in terms of more familiar concepts. You understand lightning by explaining it as electrical discharge. You understand electricity by explaining it in terms of electron flow. But what do you explain quantum mechanics in terms of? Quantum mechanics is supposed to be the foundation. There's nothing more fundamental to reduce it to. This means that our understanding of quantum mechanics might be fundamentally different from our understanding of other phenomena. We might have to accept that quantum mechanics is just how nature is, without being able to explain it in terms of anything more intuitive or familiar. We might have to accept that reality at its deepest level is irreducibly strange, violating our intuitions in ways that can't be explained away. This is deeply unsatisfying to the human mind. We want ultimate answers, final explanations, a theory that makes everything click into place. But maybe that's not possible. Maybe reality is fundamentally mysterious, and the best we can do is describe it mathematically and use our descriptions to make predictions, without ever achieving the kind of intuitive understanding we crave. Now let's bring this down to earth and talk about how quantum entanglement should actually affect how you live your life, how you make decisions, how you relate to other people and to the universe. Because if what we've discussed is true, it has profound practical implications. First, let's talk about interconnection. You've heard throughout your life that everything is connected, usually in some vague, mystical sense. But quantum entanglement gives this phrase concrete physical meaning. At the quantum level, you are genuinely, measurably connected to everything else in the universe through entanglement. This isn't a metaphor. This is physics. What should you do with this knowledge? You should recognize that your actions have consequences that ripple out beyond what you can see or predict. Every choice you make, every interaction you have, creates entanglement that spreads through the quantum network of reality. You're not an isolated individual acting in a vacuum. You're a node in a vast network, and your actions affect the whole in ways you can't fully control or comprehend. This should make you more careful, more mindful, more intentional about how you live. It should make you think twice before acting in harmful ways, because you're not just harming some separate entity out there. You're harming the interconnected whole of which you're a part, and ultimately, you're harming yourself. But it should also make you more compassionate. When you hurt someone else, you're hurting someone you're quantum mechanically connected to. The boundaries between self and other are not as solid as they appear. At the deepest level, harming another is harming yourself, and helping another is helping yourself. Second, let's talk about uncertainty. Quantum mechanics tells us that the universe is fundamentally uncertain. The future is not determined. It exists in superposition until measurements collapse possibilities into actualities. This means you face genuine open possibilities. Your future is not already written. Some people find this terrifying. If the future is uncertain, how can you plan? How can you feel secure? But I'd argue you should find it liberating. You're not trapped in a predetermined script. You have agency. Your choices matter because they collapse possibilities and create your timeline. This should make you braver. Take risks. Try things. The outcomes are not predetermined. Yes, some possibilities are more probable than others, but the improbable happens all the time at the quantum level. You might fail, but you might succeed in ways you never imagined. The only way to find out is to make the measurement, to take the action, to collapse the wave function of your possibilities. Third, let's talk about observation. Quantum mechanics tells us that observation matters. The act of measurement changes what's being measured. Applied to your life, this means that how you look at things affects what you see. Your perspective, your frame of reference, your questions shape your reality. If you look at your life through a lens of scarcity and fear, you'll collapse possibilities in ways that confirm scarcity and fear. If you look at your life through a lens of abundance and possibility, you'll collapse possibilities in ways that reveal abundance and possibility. This isn't just positive thinking or mystical nonsense. It's a genuine insight from quantum mechanics. The observer affects the observed. So be intentional about how you observe your life. What questions are you asking? What are you measuring? What are you looking for? Because what you look for, you'll tend to find. Not because reality is infinitely malleable to your wishes, but because the act of observation genuinely shapes which possibilities get actualized. Fourth, let's talk about identity. You think of yourself as a unified self with a continuous identity over time. But quantum mechanics suggests that this is an approximation, a useful fiction. You're a pattern of quantum information that's constantly changing, constantly entangling with your environment, constantly branching into different versions in the many worlds interpretation. This should make you less attached to your current identity. Who you are right now is not who you have to be tomorrow. You're not fixed. You're not trapped in your past. Every moment, you're collapsing new possibilities, creating new timelines. You can reinvent yourself because the self is not a solid, unchanging entity. It's a flowing pattern. But this should also make you take responsibility for yourself. You can't blame your past for who you are now, because who you are now is the result of measurements and collapses that are happening right now in the present. The past shaped the probabilities, but you're collapsing those probabilities into actualities through your choices and observations in the present. Fifth, let's talk about relationships. Every person you interact with is someone you become entangled with quantum mechanically. You exchange particles, photons, quantum correlations. You're not two separate entities meeting. You're two patterns becoming woven together into a larger pattern. This should make you more selective about your relationships. Who you spend time with literally becomes part of you through entanglement. Their quantum states become correlated with yours. In a very real sense, you become like the people you associate with, not just psychologically, but physically, quantum mechanically. But it should also make you more committed to your relationships. When you entangle with someone, when you build quantum correlations with them over time, you're creating something real and physical, not just emotional. Breaking those connections isn't just emotionally difficult. It's a physical severing of quantum correlations that have been built up over time. Sixth, let's talk about death. You're going to die. Everyone dies. But quantum mechanics suggests that death might not be the absolute end you think it is. The quantum information that constitutes you can't be destroyed. It disperses, spreads out, but it persists in some form in the universal quantum state. Does this mean there's an afterlife? I don't know, and I don't want to make claims beyond what the physics supports. But it does mean that your existence leaves a permanent mark on the universe. The quantum correlations you've created, the entanglements you've formed, persist even after your death. In a sense, you become part of the universal quantum field, contributing to the structure of reality itself. This should make death less frightening. You're not going to be annihilated. You're going to be transformed, dispersed, integrated back into the whole from which you came. In some real sense, you'll continue to exist as information in the universal quantum state. But it should also make your life more precious. You have this brief period where you exist as a localized, coherent pattern, as a conscious observer collapsing wave functions and experiencing reality. This is rare and remarkable. The universe has arranged itself temporarily into the pattern that is you, and you get to experience being you. Make it count. Seventh, let's talk about meaning. In a classical, deterministic universe, it's hard to find meaning. Everything is just atoms following laws, and you're just a complicated arrangement of atoms with no special significance. But in a quantum universe with entanglement and observer-dependent reality, things look different. You're not just a passive arrangement of atoms. You're an observer, a measurer, a collapser of wave functions. You're how the universe observes itself and creates definite reality from quantum possibility. That's a kind of cosmic significance. You matter because observation matters, and you're an observer. Now, this doesn't give you meaning in some ultimate, objective sense. There's no cosmic plan, no predetermined purpose. But it gives you agency. You're a participant in the creation of reality, not just a witness to a predetermined show. And that participation is its own kind of meaning. You get to help write the story of the universe through your observations and choices. So my advice is this: live as if entanglement is real, because it is. Recognize your interconnection with all things. Embrace uncertainty and use it as motivation to act boldly. Be intentional about your observations because they shape your reality. Hold your identity lightly and be willing to change. Choose your relationships carefully because they literally become part of you. Face death with equanimity, knowing you'll be transformed but not annihilated. And find meaning in your role as an observer, as someone who collapses possibilities and participates in the creation of reality. We're approaching the end of this journey, and I want to help you integrate everything you've learned into a coherent understanding that you can carry forward. Because quantum entanglement isn't just a fact about particles. It's a window into the deepest nature of reality, and looking through that window should change you. Let me recap the key revelations. Particles separated by any distance can be instantaneously connected through entanglement. This connection transcends space and possibly time. Local realism, the idea that objects are separate and have definite properties, is false. Reality is observer-dependent. Different observers can have incompatible but equally valid descriptions of events. Space itself might emerge from the pattern of entanglement between quantum bits of information. Everything in the universe might still be entangled from the Big Bang. Consciousness and quantum mechanics are the two biggest mysteries in science, and they might be related. The boundary between self and other, between observer and observed, is not as solid as it appears. What does this all add up to? It adds up to a picture of reality that's radically different from the common-sense classical view. The universe is not a machine made of separate parts following deterministic laws. It's not a collection of independent objects moving through empty space. It's not a deterministic clockwork that's been ticking since the Big Bang. Instead, the universe is a unified, entangled quantum system where everything is connected to everything else in ways that transcend space and time. It's a system where observation and measurement play crucial roles in actualizing possibilities. It's a system where consciousness might be fundamental, not emergent. It's a system where you, as a conscious observer, are not separate from the universe, but are how the universe experiences itself. This is not mysticism. This is physics. This is what the mathematics and the experiments are telling us. And if we take it seriously, it should fundamentally reshape how we think about existence. Let me tell you what I think this means for the big questions. Does God exist? I don't know, and quantum mechanics doesn't answer this question definitively. But it does suggest that if God exists, God is not separate from the universe, watching from outside. God would have to be the unified quantum field itself, the ground of being from which all possibilities emerge and into which all actualities dissolve. God would be the entangled whole of which we're all parts. Is there free will? The answer is subtle. Your choices are not predetermined by the past because the future exists in quantum superposition, but they're also not purely random. They're measurements that collapse possibilities according to quantum probabilities shaped by your past, but not determined by it. You have agency, but not unlimited freedom. You're a measurer choosing which possibilities to actualize from a range shaped by prior measurements. What happens after death? Your body decays, but the quantum information that constitutes you cannot be destroyed. It disperses into the environment, becoming part of the universal quantum field. Whether this means you survive death in any meaningful sense depends on what you means. If you identifies with your current pattern, your current configuration of quantum information, then you dies when that pattern dissolves. But if you identifies with the quantum information itself, then you never die. You just transform. Is there meaning to existence? Not objective meaning imposed from outside, but meaning you create through participation. You're part of the universe observing itself, measuring itself, collapsing its own possibilities into actualities. That's a kind of cosmic significance. You matter because observation matters, because measurement matters, because the choices of conscious observers shape the unfolding of reality.